Hi everyone. Today we're going to be talking about the significance of this thing called ozone. You probably hear that ozone is the reason you're here on Earth. It's the protection of humans against cancer. You've heard all these things, but you might not know how it works. My name's Corbin. Today I'll just be giving a simple organic chemistry lecture here on ozone. I'm going to make this for both people who are in organic chemistry now at that high of a level, but also I'll do some dumbing down for people who may not be so familiar with even chemistry. Maybe you're just someone who's curious how ozone works. So, this is Bob. Now, let's give him a little name tag here. This is Bob. Everyone say hello to Bob. Bob's a nice guy. He works a 9 to 5 on this hypothetical nice little grassy hill. And he is being subject to the big, nice, evil sun. So this is I'm not the best artist here, and I'm sorry that it's a putrid yellow color, but that's all we can afford here. So let's say Bob is sitting on Earth. Bob is, as long as he's wearing sunscreen, should be protected from the rays of the sun, so to speak. Now, you'll learn about this in a little bit, what the sun's actually emitting. But for now, these rays are being deflected by first the atmosphere, but also by Bob. Now, to understand ozone, you have to understand what the atmosphere really is. Now, when you look in front of you and you go outside, you know there's something there. You know there's oxygen. Well, there's more than oxygen. The atmosphere is a mixture of gases, and this mixture consists of nitrogen, which is N2, oxygen, O2, ozone, which is O3, and we'll go into what that looks like in a second. But we also have mixed random elements like argon gas, which is an inert gas, is just there. There's other ones too, I believe helium and trace amounts. Anyways, these are the major ones. This makes up probably 98% of the atmosphere. So there's this big soup of this just hanging out all around Bob. So everywhere there could be gas, think like helium, right? That gas will just spread out everywhere. You can't see it, but there's oxygen, nitrogen, ozone, all this stuff. Now, what's important and what we're talking about today is ozone, O3. Okay, and if you've never seen chemical formulas before, this basically says in the specific molecule there are 3 oxygen atoms. And what does that really look like? Well, how we draw things is called a Lewis dot diagram. Basically, we're going to draw the atoms. So we're going to draw 3 O's represented by O, meaning oxygen. All right, so I'll just write off to this side O3. This is the molecule we're trying to show. Now, we also draw these things called electrons, which is a subatomic particle that is found. Now, atoms can share or just hoard electrons to themselves. If they share, we draw a bond. And it turns out this middle oxygen is going to share, now he'll have 6 to share, but he's going to share with his neighboring oxygens and make a bond here and what's called a double bond here. Now, we're not going to get into the specifics of bonding and all this stuff, but just know oxygen here will make 3 bonds. Okay, so what this does is this allows oxygen here to keep 4 of his electrons. So without getting too technical here, basically the electrons are going to be dispersed like this. This oxygen to the left, now we could invert the molecule and make it the same, but just for in our reference frame here, this oxygen molecule has 4 lone electrons hoarded to itself. It's sharing 2, and it's also borrowing 2 in that sharing process. And this is actually very stable. It's called the full octet when you have 8 electrons on yourself. Again, not very important, but just something to realize for those who may know a little bit about chemistry. Now this middle oxygen, how many does he have? So he has 2 to himself. He's sharing 3 and borrowing 3 from the other surrounding oxygen. So he's borrowing these 2 here, borrowing this one, he's sharing this one and these 2, and he has these 2. If we add up how much that is, well, let's count. We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, So that's good here. Although it is making one more bond than it should, so we're gonna give this a positive charge. Okay, and then this oxygen here actually has another electron to itself that's non-bonding than we'd like. So we actually represent that like this, where it's going to hoard so many electrons. This is pretty cool when an atom does this, like oxygen. It has 1, 2, 3, 4, 5, 6. 6 to itself, 7 it's sharing, 1 it's borrowing. It satisfies the octet rule, but although it's taking one more than it usually does, we give this a negative charge. So this has a negative charge, this has a positive charge, and overall the molecule is very stable. It has a net charge of 0 because that negative charge and that positive charge can be, what's it called, canceled out, so to speak, for an overall of 0. And basically what this means is that, okay, it's stable enough molecule. Okay, so that was a little bit rough of a talk if you maybe don't know that much about chemistry and Lewis dot diagrams, but it's important to lay the foundation of what we're going to talk about. So this O3 molecule is what protects Bob from what's called ultraviolet light. So UV light, which we also denote as H nu. So that this H and then nu is a Greek letter. So UV light or H nu, that's what we're going to describe ultraviolet light as. It's a frequency of light. Now, light is a photon and it can have different wavelengths. So wavelengths can look like this. It can look very long. So if light looks like this, you might think microwave, radio wave, those kind of things, right? But as we shorten the wavelength, it rises in energy, right? Because it's going a lot faster. This is where ultraviolet light comes in. So the visible spectrum that our eyes can detect, let's say, looks like this. All right, this wave is visible. So this would be like a radio wave or something. This blue wave here, we're going to say that this is visible light. Ultraviolet light, however, looks like this. Notice how the crests of the wave are a lot closer together. Okay. When they're closer like that, remember how I said that they're raised in energy just a second ago? So if we rank these by energy, for example, this green one takes the cake, right? This one would be second, and this long wave here would be the third with respect to energy. So when something has more energy, right? If I have a truck that's going 90 miles an hour and slams into the back of an SUV, that's going to do a lot more damage than compared to, let's say, like my little Jetta car or even my sister's Mini Cooper going 60 miles an hour and slams into the back of an SUV, right? A lot less energy of an impact, right? But if we have more energy, you can cause more damage, right? Unfortunately, if you have a baby in the back of that SUV, he's probably not going to live if a truck hits him. So kind of sad, but basically, the whole idea of the whole wave talk here is to explain to you that the shorter the wavelength, the higher the energy. Ultraviolet light takes on a higher energy wave by shortening the wavelength. So that's important to talk about. So visible light that we can see is not as high in energy as these ultraviolet lights that we can't see. They're just outside of purple. The purple spectrum. So what you see as purple, just a little bit short of a wavelength than that, and you're going to get these very high energy waves. So we're going to draw it like this. So ultraviolet light is going to carry this energy with it. It's like a missile. Think about it as a missile coming in from the sun. So the sun poops out a ultraviolet light wave, and it's going right for Earth. Okay? What's going to happen most times is it's going to be deflected. So it stops here. It hits ozone. So this ultraviolet light is going to hit ozone. And we'll get into the chemistry of like what happens there. But it hits ozone and it stops. It gets transformed into something called heat. So that's why on a sunny day, things really heat up. The air heats up because it's absorbing all these different types of photons, UV, visible, all this stuff. It's absorbing it and it's heating up the air. But that's what happens here. Let's say it didn't get stopped. Let's say it hit Bob. Well, sometimes it would be fine, but what happens if you get enough UV light on you is you get cancer. Cancer basically is the loss of the control of the cell cycle, and it just makes you replicate. And like, let's just say I told you to make, let's say you're working at a Snickers factory, and I had a nice pace, okay? You can wrap the Snickers really great. You wrap the Snickers, it goes. You wrap the Snickers, it goes. You wrap the Snickers, it goes. But let's say I just bombarded you with Snickers and I told you to wrap all of them. You're going to be like, you're going to try to wrap it as fast as you can, but some of those Snickers aren't going to get wrapped. Maybe some of them get squished because you're freaking out. You're squishing stuff. Maybe some of them don't get it on it, but maybe not full. The cells that happen when it's hit by ultraviolet just and are cancer and now they're replicating like crazy is they lack that quality that our cells have, and that's why tumors grow. They just look hideous and stupid, like they have no function. That's what these tumors are, and ultraviolet indirectly causes that by damaging the DNA and therefore making it lose control. Most of the time your body will catch it, but in this case it just doesn't. So when it hits your body, it's going really fast of the energy. It hits your cell, might cause cancer. So that ultraviolet light, we don't want it to hit Bobby or it could cause cancer. So ozone here is going to help us. Now we have to get into the chemistry here. So I'm going to undo all of my precious work here and get into now the chemistry of what this is. So goodbye, Bobby. Okay, so let's talk. We have ozone. Remember, I said this was, it looks something like this, right? And what I'm gonna make a simplification here. For the two little dots, I'm just gonna draw little lines. So positive there, negative there. So here comes an ultraviolet light source, and it's coming in, and it's going to attack our ozone. Where will it attack? Well, there's something interesting that happens, and it's called a radical process. It's pretty radical, if you don't know, pretty radical. But basically, what's going to happen is this ultraviolet light comes in, and we're going to draw this as a reaction, of course. It comes in, and I'll just draw a little visual here. It's going to come into this bond and split it homolytically. So, and what that does is it looks like this. So it's going to break a bond and shove an electron onto that side, and break a bond and shove an electron onto this side. So what you're left with is it kind of breaks the molecule apart. You're going to get this here. So I'm going to draw the electrons in green, and I'll draw them as dots now because it's kind of important to see. It's going to split up the ozone into oxygen. Kind of cool, right? Oxygen, the thing we breathe, right? But also, it's going to make what's called an oxygen radical. So, or just a ground state oxygen atom. So it looks like this. Basically, this oxygen can now attack something. And maybe it might attack something, but what it does, so it absorbs that ultraviolet light to split the bond apart. So, and you would denote this if you're an organic chemist as H nu, right? Because you're saying the driving process of this chemical reaction isn't heat, it's ultraviolet light. So the ultraviolet light hits the molecule and splits it apart, but then it's going to come back together, right? There's this idea in organic chemistry called the proximity effect. If you cause a chemical reaction to occur, the most likely next step is going to maybe be an interaction between the two, if it's favorable, and in this case it is. Because what's going to happen is you split them apart, but the molecules are still right next to each other. What's going to happen now is they're going to come back together. Okay, so they're going to be split apart, kind of dramatic. They have a breakup, but then they come back together, right? Oh, I miss you, oxygen radical. And basically, if we were to draw this as, say, arrow diagram, what would happen is, well, this bit here is going to come to reform a bond. So notice here the bond was split apart. Now these electrons to this arrow is going to come back together. So they kind of give a little smooch, right? Nothing like a good makeup smooch. I don't know. I don't argue with my girlfriend. That's for weenies. So we split the ozone apart. Now it's coming back together. Okay, so we're going to reform that ozone. And I'm not going to even care to draw in the electrons. It's not important here. What matters is you took ozone and you did some process to it and you made reformed ozone. So this is actually a catalytic process. You're going to absorb ultraviolet light and then you're going to reform the bond. But for it to come back together, it's going to have to do something. It's going to have to emit some sort of energy. And this is where we have, because energy just can't be created nor destroyed. It takes energy to drive them apart. They'd much rather be together. But it took energy to drive them apart. It takes an argument in this case, like if we're thinking about people. But in this case, it was ultraviolet light. It split them apart. They have to come back together. But that excess energy just can't be in the molecule. That's not really what's happening here. It has to emit that energy. And for those non-chemists, it might be like, well, why does it do that? It just does, okay? That's a good I mean, for curious minds, that might not be so good, but it's going to go from photon energy, and it's going to get transformed into this other kind of energy we call heat. Thermal energy, right? So when something's hot, it has thermal energy. That's what it gets turned into. This is why the atmosphere heats up on a sunny day, like I said, right? You sit out in the sun, you're going to start to warm up. That's because all these cool chemical reactions are happening where it's releasing heat. Or let's say, for example, in the atmosphere, this reaction's happening. It's making the molecules very, very hot. So when it touches your skin, it's transferring that hot energy to you. So like I said, we go from ozone to ozone, but we go through this intermediate process where it splits off, it comes back together. It absorbs ultraviolet light, it disperses it as heat. Makes sense? All right. So hopefully this cool idea made sense to you. I just want to do a little recap overall. So maybe for those non-chemists, you learned something kind of cool today, but if not, all good. You know, maybe this was a little too much. I don't know. Or maybe you have some background in chemistry. I don't know. But basically, we're just going to sum it up like this. So Bobby is on his nice little hill. Let me redraw Bobby. So Bobby says, hello, everyone. He's waving with his little spaghetti hand. I don't think he lives on planet Earth, but let's say this ultraviolet light comes in and it's stopped. Basically, what's happening is that ultraviolet light, so I'm going to call that H nu, the ultraviolet light hits ozone and is released as heat. And this is where the protection of the protection of you comes in, right? If we have less ozone, this process isn't going to happen. Ozone's like a shield, right? It, no matter what you shoot at it, it's not going through. You know, unless you like shot a 50 caliber bullet at it, and it just explode. I don't know. Ozone's a good molecule for trapping this ultraviolet light, and it's catalytic. It will just continue to be ozone and have that absorption property to it. So it absorbs ultraviolet light, releases heat, stays ozone. Hope you guys learned something in this video. And before I go, Bobby's happy because Bobby has no cancer. Bob, no cancer. And one more thing before I go. Ozone isn't perfect. There, just by chance, some ultraviolet light will get in. Okay, the path that ultraviolet light takes, there's probably I don't know. I'm not an astrophysicist or an astrologist, I think. I forget what it's called, but just by chance, some of that ultraviolet light will get through and not hit an ozone molecule and hit you. That's why we wear sunscreen. And another important application of this knowledge that you have now, please understand that when you hear that the ozone layer is depleting, don't just go like, oh, this is stupid, why should I care? You should care because if we don't have ozone, we don't have protection against that ultraviolet light. So when you hear things like freons that are destroying ozone, for example, that's another radical process that you can check out. For example, if that never doesn't occur, if we don't have ozone to protect us, if we have these things that are killing the ozone, putting a ozone hole, so to speak, that's a problem. That's a real problem. That's like cancer for a lot of people. That's gonna well, first of all, it's gonna make sunscreen companies very happy, but also it's like you don't have protection for like even animals, right? What if this impacts animals, impacts humans, right? It's just not good. So please take ozone threats in our environment very seriously, because if we don't have it, we're going to get cancer most likely, or the frequency of, the more correct statement is the frequency of cancer will go up. And that's no fun. We should strive to have no cancer in America. So I hope that this video informed you on ozone. Hopefully I made it a little bit understandable for those who aren't as chemically equipped, so to speak. So have a wonderful day, guys. And again, please subscribe. I need it. Thank you. Bye-bye.